Okay, hi. I'm Tom Scholl with AT&T, and this presentation is going to go over BGP MD5, what it's used for, why it's there, and the potential for an attack vector where somebody could really throw packets at your router with an invalid MD5, and what's really the impact of it, because I don't think everyone's really stated what, if it's good, if it's bad, what's really the story behind it. So. Here's a little play on the Canadian cigarettes. They have a little bit colorful warnings than in the United States, and just a little play on that Photoshop work. So, somebody laughed, that's good. So, BGP MD5, what is it really solving? And it's really a method to authenticate the remote end of a BGP peer, which is important because you want to probably prevent your sessions from being hijacked or severed. And in addition, there's some cases where there may be misconfiguration. There's stories about where some customer maybe will turn up a T1 and note that, their BGP session was configured for an iBGP session, which is pretty bad. So, if your config's always by default had MD5 enabled, you probably shouldn't have a problem. So it's definitely a good practice to do. And in addition, it was a well-advertised workaround to a TCP/IP issue reported 2 to 3 years ago that kind of came out across the world, and we'll get into it. So the background of BGP MD5, it's really not a function of BGP. It's 18 to 20 bytes in the TCP options field. That's calculated by various things, the pseudo header, the header, any segment data, and the actual key itself. So pretty much think of it, it's a password for a BGP session. And so what about the actual vulnerability that came out a few years ago? And the issue had to do with how routers were actually authenticating a session, which was, there was a risk that somebody could try to brute force a BGP session where they could sooner or later send a reset and sever a BGP session. Another additional twist on this was you could send an ICMP unreachable message and try to accomplish the same thing too as well. And so MD5 was pushed as the workaround to resolve this, which was, well, if you need to verify the packet, no attacker would be able to determine that, so the problem would be solved. And the way it came out was a little bit strange because all of a sudden everyone started asking for MD5 at a certain time, and it was somewhere along the lines of when every network provider starts upgrading their routers within a week. So people kind of knew something was going on. And the other thing is it has some other operational complexities. BGP MD5 is not easy for everyone. A lot of automation, a lot of tools, OSS types of things that provision customers, they had to be modified to support MD5. Another thing is when you do have customers with MD5 or peers, for example, where do you store that data? You store it in a text file, some sort of database. Storing it somewhere is kind of a risk as well. And then how do you actually transmit it, exchange the key with your peer? I mean, do you on the telephone? Do you send it in email? If it's in clear text, what have you really solved? And another thing is, how do you actually generate the password? Are you just randomly making it up? Are you going to any of the, if you Google around for a password generator, you can find plenty of websites that'll generate it for you, but who's saving all that data? You never know. They could look at the source IPs and some HTTP access log and perhaps start using that. So how to properly exchange MD5 keys. So if anyone remembers the TV show Get Smart, there was this thing called the Code of Silence. And, is this the way we have to do it? And in Pig Latin as well, just as a twist. But it didn't really work that well on the show, so it probably wouldn't really work here. So what's the real impact of, MD5, which is it's the router is basically looking at the TCP header and has to determine if it's proper or not. And router obviously has to do a bit more additional work, so that's additional load for the route processor, which is already busy doing other critical tasks such as best path decision processing, your IGP, management, a lot of other things. The less work you have to give the route processor, the better. So the idea is what happens if an attacker would happen to spoof, just basically flood your router with incorrect MD5 hashes, and could they make your router CPU utilization go up, and that would then impact other protocols on the router, other BGP sessions, your IGP adjacencies, things like that. So generally, what's the impact of someone actually taking down the router? And it kind of brings up another question, which is why should somebody be sending spoof packets to your router in the first place? Why are they even getting there? And that's a whole other issue aside. And shouldn't everybody be doing BCP38 and filtering this? Well, the reality is not everybody does that. So, and in some cases, it's just not feasible. When you have shared LANs, a /23, a /24 at a public exchange point, it's a little bit harder to do that. And the actual MD5 as a whole, is it really the best solution going forward to secure BGP sessions? I mean, it works now. Is the best thing that we should do going forward? So some of the other options, for example, is the Ttl Security Check, or GTSM, which is a really nice way to say, not looking at layer 4, but looking at layer 3, which is I'm going to look at the IPTTL and say, did this really come from my neighbor? And it does this by when you transmit BGP packets to a neighbor, it just sets the highest TTL value possible. The neighbor expects to see it at a certain limit or above. And it works really well since no one could really spoof that from 6 hops away. Another option is, well, perhaps we can tunnel it. Should we take a BGP session and put it over some sort of other transport mechanism, Ethernet.1Q, frame relay DELC, a GRE tunnel, MPLS pseudo wire, perhaps just a route reflector somewhere, other kind of hacks like that. So another option is eBGP multi-hop, right? So this is, I'll get into this later as to why this really doesn't work that well. And, anti-spoofing ACLs, well, if you could stop all the spoofing, then there wouldn't be a problem, but, well, that's another story. So I tested a variety of platforms or whatever I could get my hands on, and some Cisco GSRs, a few of the higher-end Juniper boxes, and a 6500. You're running relatively code that's been released within the last several years or recently. And the types of attacks we're looking at was, well, let's have you have a BGP session with MD5 enabled. What happens when you send incorrect hashes? What happens when you send none at all? It's just a regular packet. What happens when you have BGP enabled with the Ttl Security Check and doing the same kind of traffic as well to it? So some of the results that I found was that some platforms, they'll actually, when they receive a packet with invalid or no hash at all, they'll log it, which is kind of bad because you're having, if you have, thousands of packets per second, there's some sort of logging mechanism within the router that's constantly logging that it's received one bag packet for each individual one if it doesn't actually try to aggregate or suppress, this over time. And in some platforms, this could be even worse if you're doing something like logging to console, in which it's, firing this out the console port, which isn't really that great either. And that could actually be the bulk of the CPU utilization is actually used on this rather than anything related to TCP session tracking. Another thing is some platforms that really can't do the TTL check in hardware. I mean, it sounds like a great feature, but no one really had anything in the hardware to actually analyze the IPTTL value. No one, not many people requested it, so vendors probably didn't add it, I'm assuming, for many years. So it's actually done in, the route processor, for example, which really doesn't buy you all that much. And the testing has shown that it really had kind of the same impact as, doing MD5 or not. And just one example on a lower end, GRPB, it actually, at a low speed attack, it did increase the CPU somewhat significantly. And then another thing is some platforms actually examine the MD5 hash before the IPTTL. So let's say you had a session that was enabled with MD5 as well as the IPTTL check, and you said something with clearly the wrong TTL, clearly spoofed, and you had the incorrect TTL or MD5 hash, and the MD5 hash would be alerted as, this is invalid. So it's obviously checking MD5 before the IPTTL, which doesn't make much sense. So the actual difference between having a signed packet and one without was really not that much. And in fact, in most cases, it was less than 10% of CPU utilization of an increase. So, modern hardware, it really didn't make it that much of a difference. So, I mean, there's some people who've commented, that, MD5 is a valid attack vector. I mean, I'm just not seeing it. Perhaps, on lower, platforms, this might be the case. It just, the real issue here is that you have lots of packets per second going to a route processor, and it's touching something internal to the system that it shouldn't. And, using the TTL checks within software that some vendors do support really didn't buy you that much. It was the same impact. So some of the other alternatives, would be the TTL checking if it was done in hardware. And some of the higher-end router platforms could do this. CRS1 is reportedly can. Some of the higher-end Juniper boxes as well can do it. Anything else, I'm not really that sure if anybody else can do it. So I'd be curious to find out if this is even a feature possible or is planned. So some of the other alternative methods to do BGP. So if you can't secure it with the way that's already in place, what else can you try? You could try eBGP multi-hop, for example, which you're really not really hiding anything other than the IP addresses that are used within the TCP session. So you may source it from a loopback interface, or you may add an additional loopback interface. All it does is hide it, and sometimes that doesn't always fix it. Somebody can log into, may have a looking glass or a route server, and they can actually learn those BGP addresses. If you do use a loopback, well, most people's routers have, DNS, and NSLOOKUP will clearly reveal what the loopbacks are. So it's not that hard to figure out sometimes. And, with multi-hop, there's really no failure detection. If it's crossing multiple devices, somebody has a switch in the middle, may not detect when there's a failure. So that really doesn't work that well. The other issue is you want to do a separate interface or tunnel. It's additional complexity. You're doing something that may be a one-off. Not every peer can do it, so you're supporting something unique. And plus, if you're learning it over a different session with different addresses, you're going to have to rewrite the BGP next hops, which is yet another one-off, and it doesn't really work that well. So let's go back to really what the bigger picture is. Why are these packets even hitting your route processor in the first place? So the real problem is in MD5 or IPTTLs, why are they getting there? Obviously, somebody's spoofing them. Is there a way to actually fix that? Well, so if you have two networks that pair together, let's say it's a service provider and a customer, one option, some networks have done this, is they don't redistribute the customer's directly connected interface, which is a really great plan, except there's some customers who have to source, let's say they run NAT on their WAN uplink. Well, in that case, it breaks it, and you may have to number the customer out of a different space. Some routers, you could do an egress ACL, for example, towards the pair, and when you generate a packet from the route processor, it actually bypasses that ACL. So that would actually work, but not everybody's implementation is the same, and to do egress ACLs that it may be unique and doesn't always work as well. So another option is, what happens when you have Internet Exchange Point address spaces? Should we perhaps add this into, if you do have infrastructure ACLs, should this be considered a part of it? Why allow the packets even to go there? Do people have business pinging things? Why should that traffic even go there? But of course, what do you do when you have private pairing sessions with another pair, for example? You can't, typically people trade on one and off. I use my address for this /30 or 31. They use theirs. You can't update all your customer-facing ACLs to do this. It just does not work. Another option is, and this kind of covers a lot of this, is just as brought up earlier, why are you redistributing Internet Exchange Point address space within your IGP or IBGP domain? Why even do that in the first place? Don't even let people route to it. Is that feasible? It possibly is, but given that the fact that people are already originating Internet Exchange address space on the Internet today, it probably is not going to happen. So really, what are your options that you can do? Well, if you do have the hardware that supports it, you can actually, do the actual TTL checking within, hardware, and it works, and you just have to coordinate it, and hopefully the other side supports it as well. Like I said, there's not very many platforms that can do that. I'm not sure if there's any others or on the roadmap for anybody. And then, as a word of caution, control plane policing that's implemented in the software really doesn't always buy you that much. So, there's a lot of various hacks that you could do, but the hardware is just not there today. So that's about it. So, any questions?
No questions? I'm surprised.
No.
Amazing. Okay, well, if there's no questions. Thank you, Tom.
Okay.